Hello everybody, we're back in another video. In this video we're going to be looking at the electrical concept or electronic basically concept. Let me clear this. It's a electronic um electronic concept of redox reaction. So what did we learn in the last video, right? We learned about the classical concept. You can go and see the last video. It is very short, 7 videos, so you can just go and see it, right? So we're going to be looking at what is the electronic concept. We looked at the limitations of the classical concept. It only works in atomic level. It cannot explain gain or loss of electron. So what exactly can explain gain or loss of electron? That, my friends, is the electronic concept of redox reaction. What is the electronic concept of redox reaction, right? So it involves, now let me give you guys a definition in terms of electronic concept. Oxidation. What is oxidation? It's a loss of electron. Oxidation is basically defined as the part of reaction in which free, like atoms, ions, or atom present in a molecule, let's say, undergoes chemical change by loss of electron, right? Only by loss of electron. Now what is reduction? I told you, polar opposites, oxidation and reduction. So what it might be is gaining of electron, because oxidation is loss of electron, right? So reduction is defined as basically the part of reaction in which like free atoms, ions, or atoms and molecules undergoes like chemical change by gain of electron, right? And we're going to be looking at this example, right? In this, the charge of Na, which is the sodium, is 0 because it's in a free state. In a free state, the elements have the charge 0, right? That is basically a rule you have to learn in the oxidation number. Basically, while finding the oxidation number of something, you have to learn this rule, right? In a free state, Na has the charge 0, right? But now that you have Na has lost the electron, right? It has lost the electron. It has gained the charge Na plus. This is the charge. All right. I could not put it in a superposition, so superscript position. So I could not really do that. So you just have to understand this as Na plus, right? And you can give other examples as well, but this is the one example you can give. Right? You can also get the Cl example, Cl minus though, right? If a Cl minus loses the electron, its charge gets converted into 0, because minus, how did it gain the minus charge? By gaining the electron, right? I gave you the example how to find the minus charge, negative charge or positive charge in the last video. Electronegative species, electropositive species, gifting or giving the gift, right? I gave the example in the last video. So basically Cl minus gets converted into Cl 0, the charge 0, if it loses the electron, right? Then we can also give the example of Al, right? What is Al? Aluminium. So if it if it loses 3 electrons, its charge is Al plus plus plus. That's basically in ionic level, right? This is the ionic level concept, right? But this is only the surface level example. We're actually going to be looking at the chemical reaction where the oxidation and reduction takes place simultaneously. This is not a redox reaction. This is not a redox reaction because oxidation and reduction does not take place simultaneously. This is a redox reaction because in this, oxidation and reduction takes place simultaneously, right? So what can you look in this example, right? Zn plus CuSO4 gets converted into ZnSO4 plus U. Now you have to convert this in ionic level, right? Like basically like this, right? You have to convert this in terms of ion. Zn plus Cu plus plus, which is the charge, gets converted into Zn plus 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 Cu. What? How did it gain the plus plus charge? Now that is because of SO4. SO4 has a charge of -2, right? -2 charge, and in this CuSO4 the net charge is 0, right? That means the charge of Cu should be +2. So +2 minus 2 gets converted into 0. And even in this Zn, +2 minus 2 of SO4 is converted into 0. So you just take out the SO4. Now SO4 is basically the spectator ion. I'm going to be explaining that later on, but in this process you just need to know that you have to convert this in terms of ions, right? Zn plus Cu plus plus gets converted into Zn plus 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 Cu. Now what happens in this? Zn gets converted into Zn plus plus. That means it has lost 2 electrons. What is the loss of electron? Oxidation. Bam, that's done. So Zn gets converted into Zn plus plus. It undergoes oxidation. Cu plus plus gets converted into Cu. That means gains 2 electron. That means that is basically reduction. That's it, right? So what is Zn? Is it a reducing agent or oxidizing agent? Oxidizing agent? No. It's actually a reducing agent because Zn undergoes oxidation. And as I have explained it in the last video, oxidizing agent and reducing is basically, reduction is basically the same. If you are undergoing reduction, you are an oxidizing agent. If you are undergoing oxidation, you're a reducing agent or reductant. It's that simple, right? You can check the last video for more. Now we can also see the electronation or de-electronation, but before that I'm going to be explaining what is spectator ion. In this case, spectator ion is SO4, right? Now what is spectator ion? Basically they are like those ions which are removed from both sides of the equation, right? In this you can see that SO4 is removed from the left hand side, SO4 is removed from the right hand side to get a net ionic equation. What is this? It's a net ionic equation, right? And SO4 also do not involve in chemical change, right? It is involving in chemical reaction, but it's not involving in any kind of chemical change. So you can get the definition in this way, right? Those ions which are removed from both sides of the equation to get the net ionic equation and do not involve in chemical change are called spectator ion, right? Now we're going to be looking at electronation and de-electronation. It's simple. Electronation is the process which involves the gain of electrons. You know that. De-electronation is the process which involves the loss of electrons. So de-electronation is oxidation. Electronation is reduction, right? It's pretty simple. It's basically getting mummified and getting demummified. It's that simple, right? Now next we are going to be looking at oxidizing reducing agent in terms of electronic concept, basically a definition, right? So oxidation is the losing of electrons, so oxidizing agent should be gaining of electron, right? Those reagents which gain one or more electron in redox reaction are called oxidizing agent, and reducing agent are those reagents which lose one or more electron in a redox reaction, right? Basically the polar opposite. Just remember the word polar opposite in redox reaction and you have known everything, right? Now what are the limitations of this electronic concept? Why do we need oxidation number now? We have already known what is classical concept, right? But classical concept is not used in this. And electronic concept is used in this. Now why do we need oxidation number? Why can't we use this process in other kind of chemical reaction? Well, first reason is this concept is only limited for ionic equation. So basically if you can convert this kind of equation in this ionic equation form, you can only use the electronic level in this kind of equations, right? And it can also not explain the process of oxidation and reduction in other covalent compounds. It can only be explained in ionic equation, not in covalent level, which is where oxidation number comes, right? In the next video we're going to be looking at oxidation number, but for now this is the end. I hope you guys revise this electronic concept. It's very easy if you have understood the basics, right? So we're going to be looking at oxidation number next, and I hope you guys stay